In the previous video, we looked at an example of simple logistic regression. I showed you that the outcomes from simple logistic regression are not very startling. They're easily calculated just by looking at the table of the frequency of the various outcomes. We can calculate proportion success, we can calculate the odds of success, we can calculate the odds ratios of success. But what I showed you is that we can get those exact same effect size estimates using the parameters of simple logistic regression. If that's as far as it went, there would be no need to have simple logistic regression. We could just calculate the proportion success, the odds of success, and the odds ratio using the frequencies in our table of frequencies. But the real power of logistic regression is when we add additional variables, and that leads us to multiple logistic regression. Here's an example in which I've added one additional variable. So we now have one categorical response variable and two explanatory variables. Now, the explanatory variables can be either categorical or quantitative, but in this example, it's going to be easier if I stick with categorical explanatory variables. I have done an instructor model report for you in which I switch to quantitative variables, so when you're done watching these videos, make sure you take a look at that. In this case, the categorical outcome variable is again whether the student passes or fails. But the two explanatory variables are socioeconomic status, defined here as high and low, and the teacher perception of whether the teacher believes the student is ready to take the test. So ready and not ready are the two values of that explanatory variable. So we have one categorical response variable, two categorical explanatory variables. I've loaded the ready data. You can see there are 742 observations. If you added up all the frequencies in the table, you would find 742, and we have three variables. So when we look at the data, we have the outcome variable coded as 1 for pass, 0 for fail. We have perception of the teacher coded as 1 for the student is ready, 0 the student is not ready, and we have SES coded as 1 for high, 0 for low. So as I go through here, if I go far enough, you'll see all the various combinations of those variables appear. Simple logistic regression is based on one predictor. Multiple logistic regression is based upon multiple predictors, and look at the familiarity of this formula. Beta 0 plus beta 1 x1 plus beta 2 x2, and so forth, all the way to our last beta x. On the left-hand side of the equation is where things are different than what we're used to, although we did see this with simple logistic regression. It is the natural log of the odds. So the natural log of the odds are equal to this linear combination of parameters that we must estimate multiplied by the explanatory variables. Now in the example that I'm showing you, we have beta 0, beta 1, and beta 2 because we only have two explanatory variables. Let's go ahead and do some analysis. I'm going to set up glm.out to be an object, and I'm going to use the generalized linear model function again, just like I did with simple logistic regression. What's different here is that I'm modeling outcome as a function of SES plus perception. Those are the two explanatory variables. Everything else is the same. It's the binomial family, more specifically the logit. And the data here, we're using the ready data. Let's go ahead and get this. And now let's look at the odds ratios. Remember that to get the odds ratios, all you have to do is take e raised to the power of the coefficients. So there are the odds ratios. Let's take some steps to figure out what these odds ratios all mean, and you'll see they have a very ready interpretation. First, to show you how this works, I'm going to create a new data set with one of every possibility for SES and perception. Now, what I'm doing here is pedagogical. If you were actually doing your own logistic regression, you don't need to do this. You can stop with these odds ratios right here. There are a couple other steps that later on I'll show you that you can take for some additional information, but you don't need to do what I'm doing here. I want you to clearly understand that what I'm doing is simply demonstrating at this point. This is not what a researcher would do. Okay, so SES can be either 0 or 1. Perception can be 0 or 1. If you look at what I've done every combination of SES and perception. 0, 0, 0, 1, 1, 0, 1, 1. So I'm going to go ahead and calculate those. And then I'm going to create a data frame from this. So we'll have this ready combs, which basically gives us every combination for perception and SES. All right, now we can obtain the probability of passing using that predict function that I showed you earlier. And I'm going to do that for ready combs for the response variable. And here's what I get for the probability of passing based upon our particular data. Our first one here is for the first combination that we had of low SES and the teacher thinks the student's not ready. There's a 28% chance. The next one, the teacher thinks the student's ready, but it's low SES. There's an 83% chance of passing. The next one, high SES, the teacher thinks the student's not ready, 37%. And then the final one is that the teacher thinks the student's ready and it's high SES, an 88% chance of passing. So let's get the odds ratio for passing the test when judged as ready compared to not ready for low SES. So ready, remember, was right here for low SES in 2. So I'm going to take the probability of passing divided by not passing. And then not ready was in 1, so I'm going to take the probability of passing divided by the probability of not passing for not ready. Then I'm going to put those in a ratio in order to get the odds ratio, and let's see what it is. It's 12.45. You might glance up here and you see that 12.45 is what we got when we took e to the beta 2. 12.45. So again, how do we interpret odds ratio? The odds of passing are 12.45 times higher if the teacher thinks you're ready. Now that was for low SES. Let's do it again for high SES. So here I'm doing the exact same thing. I'm taking the ready, which is in 4 for high SES, divided by failure. I'm looking at the pass rate for not ready, divided by failure for high SES, and let's see what we get. We get 12.45. So the coefficients that you're seeing when we take e to the power gives us the odds ratio for that variable as though the other variable was constant. In other words, it didn't matter whether we used high SES or low SES. The coefficient for SES and perception provide us the odds ratio while holding the other variable constant, and that should sound familiar, just like multiple regression. So what we say is the odds of passing when the teacher thinks you're ready are 12.45 times higher than when the teacher thinks you're not ready, and that depends not on what the SES is, because that's holding the SES constant. So now we could interpret for SES using the same logic. Let's hold the teacher perception constant. If you're at high SES, the odds are 1.56 times that you will pass than if you were at low SES. So that's how we interpret these coefficients. Pretty straightforward, isn't it? Let's see what we can infer from these data. So I'm going to go ahead and run a summary. And when I run the summary, notice SES has a low p-value when we compare the estimate here. And the estimate, notice, is not the odds. In order to get the odds ratio, you have to do e to that power. But nonetheless, the odds ratio is a function of this coefficient, and so we can utilize this same p-value over here. So it's under 0.05 if I'm going to use 0.05. Remember, I don't like binary decisions, but I like the fact that this is low. And perception, look at that. That's a whole bunch of zeros before we ever get to that 2. So that is strong evidence that the teacher's perception of whether or not the student's ready to take the test is certainly going to be related to whether or not they pass the test.